All right, to section 7.2. We're going to look at continuity, and we're also going to look at our basic function graphs and their points of emphasis. So continuity has a formal definition which requires some concepts from calculus, so we're going to go with an informal definition here. A function is continuous over an interval of its domain if its hand-drawn graph over that interval can be sketched without lifting the pencil from the graph. All right, so of its domain, here's an example. The domain goes from negative infinity, and I can still touch up until 2, then I can go to 2 all the way to infinity. So technically, this graph's domain is all real numbers. But if I trace it and I have to stop and jump and pick up my pencil and start up again, I have a point of discontinuity at x equals 2. So this is not a continuous graph for its entire domain. Now, if they give you a part of the domain, so let's say they just wanted to go, okay, for the interval bracket 2 comma to infinity, are you continuous? Well, that's just this part of the graph. Yes, I'm continuous for that part of the graph. All right, so make sure we understand how that looks. All right, determining intervals of continuity. Here we have a parabola. There's no break, so my continuity is all real numbers, negative infinity to infinity. Here's a line, but it appears that we have a hole here at 3, 1. So we have a break in our graph. That's going to be a point of discontinuity, and we describe that by writing this down as almost like you were doing the domain. Open interval from negative infinity to 3, union open interval 3 to infinity. So by having this 3 here, it shows that it's not part of being continuous. Now, if we went backwards to this graph and we wanted to write out the continuity intervals, it would be negative infinity to 2 as an open interval, union bracket 2 to infinity. So by seeing that break at the 2, just like we have this 3 here, it shows there's the point of discontinuity. All right, our graphs here, our basic functions. The identity function, which I prefer to call linear function, this is very, very specific. The identity function to me stands for the following. It's the equation where your x and y's are identical, and that's this line right here. And that's x to the first. I prefer to make this a little bit broader by calling it the linear function, so I can have any positive slope for a line, any negative slope for a line. So it kind of broadens our description of a linear function. Our domain and range, all real numbers. Our f of x equals x is going to be increasing. As you read the graph from left to right, it's constantly going uphill, and it's always continuous over its entire domain. There's no breaks. A squaring function, or the quadratic function, f of x equals x squared. We just bumped up the exponent by 1 to make it a 2. Pairs every real number with its square. So whatever x you choose, you're going to square it. The graph is always a parabola. And it changes from decreasing to increasing at the point 0, 0, which is called the vertex. So if we wanted to, again, plot some points, here's my t-chart. Not a big fan of t-charts. I'm going to show you a great way to take care of this later. Negative 2, I square it. Positive 4. Negative 1 squared, 1. 0 squared, 1. 1 squared, 1. 2 squared, 4. We plot those points. There's my graph. The domain, all real numbers, except now for the range, we've been cut off. We have no negative values. We can touch the 0, and then we're going up the y-axis. So that's bracket 0, comma to infinity. Here we have a decreasing part of the graph. As you read it from left to right, that's going to be decreasing. So that's the open interval from negative infinity to 0. And it increases on the right side from 0 to infinity. Again, we are continuous on its entire domain from negative infinity to infinity. All right, next we have x cubed. This will probably be the highest power we look at for our basic function. This is where we're going to cube all our x values. And again, now the point 0, 0 has something strange happening. At 0, 0, we're going to have a part of the graph that opens downward and a part that opens upward. And that point where it changes is called the inflection point. So if you plot some points, -2 cubed, that's 3 negatives, so that's a -8. -1 cubed is -1. 0 cubed is 0. 1 cubed, 1, 2 cubed, 8. So we plot those points, draw my graph, and here is my point of inflection at the origin. On the left side, this part of the curve is opening down, if you will. So we call this, another name for this is concave down. Here, when it opens upward, we call that concave up. And where at the point at where it changes from one to the other is the inflection point. And a way you can figure out where your inflection point is remember we talked about the tangent line in the previous class. All right, so I'm going to go grab that graph. I'm going to bring one of these in here, and I'm going to do another demo of this real quick. So I'm going to go back to this one, and I'm just going to change this real quick. Let's change it to a cubed. All right. Oh, I don't have my tangent line on here. Doggone it. Okay, I got to go back to this one. I'll change this one to a cubed because I have the tangent line on this one. Get rid of that too. All right, there's my x cubed. All right, so here we are. We're going to move our point around here. Now, I want you to notice something with this tangent line as I move. All right, as I'm moving this, notice what happens. Going to go back, and it happens when it gets to 0, 0. All right, everybody see it? You see it? You see it? You see it? I can't hear you. Okay, here's the key. Notice that the tangent line, when the graph is increasing here and it's concave downward, it's opening down. The tangent, whoops, come back here. The tangent line is above the curve. Now, when I get to 0, 0, watch what the tangent line does. It's going to cross the graph. So now the tangent line is now officially, after 0, 0, now the tangent line is below the graph. So when you go from below the graph with your tangent line to above the graph, at that point right there, that's your point of inflection. All right, I knew that graph would come in handy again. Okay, domain and range, all real numbers, just like x to the first power. And you're going to see a pattern with your x's to powers here in just a second. X cubed is always increasing and continuous, just as it was for x to the first. All right, next we're going to look at the square root function. So here we're looking at the principal square root, which means this answer is always positive. And therefore, we cannot take the square root of a negative number because it has to be a real number. We don't want any imaginary numbers here. So that's going to affect our domain to the point where we can take the square root of 0. We can take the square root of all the positive numbers. You just can't take the square root of a negative number in the real number system. So we'll start at 0. Square root of 0 is 0. And you notice I got all perfect squares here, so it's easy to take the square root of those. So we'll plot those points, 0, 0, 1, 1, 4, 2, 9, 3. There's my square root graph. And if we take and copy this domain down, and your range is going to be affected, it's going to be the same. because there's no negative y's for a possible value. The square root of x function increases on the interval of its domain. Notice the change from the domain, bracket to parentheses, because increase and decrease are always open intervals, and is continuous. Now notice it's a bracket 0 to infinity. We're touching it and we are continuous. Next we have the cube root function. Well, this is the inverse of x cubed, so everything is going to be reversed. So that means I switch my x and y's around. So if you notice, when we talked about the cubing function, if you look back in your notes, -8, -1, 0, 1, 8, we're over in the y column. Now we put them in the x column. Now we take the cube root. We're going to bring the x values from the cubing over to the y. So this would be a -2, -1, 0, 1, and 2. Plot those points. And there's my cubic graph, if you will. It's been flipped over the line y equals x. So if you draw in that identity line, which cut the graph in half diagonally at a 45-degree angle, that cubing function has just flipped over that line, and that's its inverse. So everything stays the same as the cubic function, x cubed. Domain and range are all real numbers. I will still be increasing, just increasing slower. I'm still continuous over the entire domain of -infinity to infinity. Now, next we're going to talk about absolute value function. Now, you were probably told that the absolute value of x is always a positive answer. However, if you had a really good college algebra teacher, they defined it as a piecewise function because it's really two different functions, both linear functions. So when you have an x value of 0 or a positive value, you will have the line y equals x. That will be this line right here going up through quadrant 1, cutting it in half diagonally. But when you have negative x's, you have to have a line coming downhill. You need a -1 for a slope. So if I take -8, which makes this inequality true, I'm going to go -8, which makes that a +8. I take -1, which makes this inequality true. -1, +1. 0 is now in this inequality. That one's true, so now it's just 0. 1 is greater than 0, 1. 8 is greater than 8, 8. And then we draw in, I'm just going to put in those 3 points because my 8s don't fit on here. And there is my V-shaped graph. It is decreasing from left to right. Right here, when you have a -1 for a slope, so we're decreasing from -infinity to 0. And we're increasing from 0 to infinity. Guess I kind of skipped over the domain. That's okay. Here's our domain, -infinity to infinity. And the range, very similar to our parabola, where the parabola x squared was not allowed to have negative y's. Absolute value does not have negative y's either. It is continuous. Even though you trace it, you stop, but you don't pick up your pencil. We're still good. All right, next we have our piecewise function. Now, so we're going to kind of pick up with the piecewise function that defined our absolute value, but now we're going to put other functions in here. Now, one first thing you should notice is that there's going to be certain rules for your domain. We call these domain restrictions over here. Now, instead of making a T-chart like this and filling this all in, it's time to